Hey everyone, I would like to say welcome back. We have another video here. So while watching this video, you should have with you in front of you a copy of the formula sheet that I gave you and a copy of the problems that we're going to be examining in this video. So this whole idea of problem solving in this situation is formula based. So we're essentially trying to find the formula that will work for our situation and use the formula to solve the problem. So that's the very first thing, is when we examine a situation, we want to identify what formula we are using. So we're looking at this. I'm eager to cook my wife and kids a nice beef pot roast. So we see here that the beef pot roast is cooked at a certain temperature, and the room temperature is 74 degrees. Take the pot roast out of the oven, and after 5 minutes it's now at 215 degrees. The question is, how long will it take for the pot roast to be safe to eat, assuming that 120 degrees is the safe temperature? So looking at this, what we would be using here is Newton's law of cooling. And what Newton's law of cooling examines is, it's the temperature of an object and how the temperature of the object decreases relative to the surrounding temperature over time. So typically, if we were to graph these situations, they would often look like this, like that, where our point here tends to be the surrounding temperature. But we see from our formula sheet and from above that we have a formula of temperature of time as to time equals the temperature of the surrounding area plus okay. So remember, looking at this, we know what T sub S is, we know what T sub O is, and K is just this kind of constant that is different for every object. So we know now what formula we are using. So the next thing I would recommend is making a list of what we know. So the initial temperature, our T sub 0, our initial temperature is going to be what the pot roast was at the very beginning, which is 375 degrees. Okay? And we then see that 74 degrees is the room temperature. So we would classify that as the surrounding temperature. Leave with degrees here, sure. All right. Then, as we continue reading, we wait 5 minutes, and then the temperature is measured to be 215 degrees. So how we could write this is the temperature after 5 minutes is 215 degrees. Okay. How long after taking the pot roast out of the oven will it be safe to eat, or will it be 120 degrees? So our question here is, for what time will the pot roast reach 120 degrees? Okay, so let's see. Often, ideally we have everything that we need, but often we're not given something. So let's just see. So T sub S, we have, let's go and write this down actually. So T sub S is 74. Our T sub 0 is 375. T sub S again. E, we don't know what negative K is. So the t, and notice I left the left side here empty as well. That's where this will be used. So this kind of data value. So at 5 minutes, we know what this whole thing will equal. Okay, so we have everything in, and notice we do not know what k is, and we will need to find k in order to figure out the time it will be to get 120 degrees. Okay, so understand we need this value before we can truly answer the problem. So this is an exponential equation that we just have to solve. Remember, with exponential equations, we're trying to get our exponential term alone. So let's just do some simplification here. 375 minus 74 is 301. Okay, so then this is one group, so I'm going to subtract the 74. So in doing so, we get 141. I'm going to go ahead and rewrite the exponent while we're at it. Okay, so then the exponent's not by itself yet, so we have to divide by 301. So when we divide by 301, we get 0.4684. Okay. So in this, if I have an exponential function, I need to take the log of both sides. So log base e, or just natural log. Okay. So we know what happens here with our properties. This right side becomes just negative 5k. And leave this natural log of 0.4684. And we can quickly see that we divide to get k. So when we take the natural log of 0.4684 divided by negative 5, we get k to be 0.1517. All right. So that was just k. So now we can go back and figure out the time it will be for this pot roast to reach 120 degrees. So to do this, I'll just divide the problem here. To do this, I'm having to start back at the very top again. So now we need to know when will our object reach 120 degrees. We have 74 again. The 375 minus 74 remains the same, so I'm just going to put 301, save us one little step. E. We now know what k is, so it's going to be negative 0.1517, and then t. All right. Okay, so it's again, we have an exponential function, so we move 74. You guys are probably hearing my little boy in the background. We have been all over the place past week. So we haven't been home at all. So he's just excited to be home. So you get 46. Okay. So we divide by 301. When we divide by 301, we get 0.1528. Okay. Then we take the natural log of both sides, just like before. This is a long problem, but most formula problems, if we're given everything that we need, they are extremely quick. So it's either these problems are extremely quick, or these problems are rather long. There's little chance of having one that's just, I guess you could say, average. So we get -0.1517, and we divide by -0.1517. All right, so we get natural log. Okay, we find we get 12.38. Okay, so understanding what this means is, you know, the whole situation was, when will it be safe for my family to eat this pot roast? Well, according to our formula for Newton's law of cooling, in our work here, we see that it's been roughly after, we can round up, after 13 minutes. And that would be how we would close the problem. I want to say this, Newton's law of cooling is rather interesting. You do look at it, I believe, in physics and maybe a little bit in chemistry. I'm not sure about chemistry, but there's more to this formula that you kind of examine as you learn more and more calculus. But for now, this is just the most basic, where it looks at the original temperature and the surrounding temperature. Okay? So, on to the next one. Now we're examining something that is interesting. That's just earthquake magnitude. There's a formula for this, a formula that examines the magnitude of an earthquake and the energy that it exerts. So the formula for the magnitude of an earthquake, again, looking at our formula sheet, looking at above here, is 2/3 log of E over E sub 0. Okay. So we see from this whole problem, we find that it released, the atomic bomb dropped in Nagasaki, and I think it's released about 1.34 times 10 to the 14th joules of energy. Joules is the units for energy. What will be the magnitude of an equivalent earthquake that released that much energy? Okay, so we see on our formula sheet that E sub 0 in this situation, in these situations, E sub 0 is always going to be 10 to the power of 4.40, always. So that's kind of nice. So here the energy that we were saying that this earthquake exerted is 1.34 times 10 to the 14th. Okay, so while I'm looking here, I'm trying to find the magnitude, and there's only two things that I need, and I have both of them. So this is going to be a really quick problem. All right, so this magnitude, I'm hoping that we know what the base of this log is, since it's not written. Hopefully it doesn't need to be said. Okay. So with that, we go to our calculator, and we just can type it in. So we have 2/3 log of, let's see, I'm going to do this. There we go. 1.34 times 10 to the power of 14, and then 10 to the power of 4.40. All right, ready? Ta-da! And we find that the magnitude of this earthquake is roughly 6.5. And I've gave you this nice chart to just kind of go off of. According to this, a bomb or an earthquake similar to that of Nagasaki's energy release is roughly 6.5. So it some serious damage in populated areas. So that's kind of pretty interesting just to see how the two relate to each other. So again, this is a perfect example how if we are given everything, these problems can be really easy. All it's a matter of knowing what formula we're using and writing everything down. Okay, so then let's see what we have next. Yes. So this problem, this is a nice one. Since 2013 or 2003, a Japanese scientist announced an effort to bring a fossil back to life. A nearby specimen. We found that a nearby specimen was found to have 28.9% of the amount of carbon remaining. So how old is this specimen? So carbon-14, how old is this specimen? It should be very, very obvious what we're looking at in terms of formula-based. Carbon-14, immediately with carbon-14, there's only one option here. That's it. Okay, so here, so looking at this, A and A sub 0, it's the amount and the amount initially. We're not given an amount here of this specimen, beginning or right now. It's just we're given this percentage, and I have found that that's actually common. That we only know the percentage that's remaining. So how do we do this when we don't know the amounts? Because this is just a percent. How do we do this? Well, what I can tell you is, first of all, let's think of this percentage as a decimal. That's 0.289. And with that decimal, let's think of this as a fraction. Or you do that out of 1,000. So this, okay, we have a fraction. I'm going to take this formula and divide it by a sub 0. So I'm simply going to remove a sub 0 over here. I'm going to rewrite it. Okay. So in this, this fraction we have is the fraction we see here in the formula. The amount initially, or so the amount we have and the amount initially. So it's like 28.9 out of 100. Okay. Which makes this problem rather interesting because it's an exponential equation. How do I know it's an exponential equation? Our variables in the exponent. Nothing is with this term, so I can immediately take the natural log of each side. Okay, so in doing so, we see that we find negative 1.2413. Okay, and then we get just negative 0.00011216, and we divide. And we get roughly 10,000 10,208. And this is years. So, knowing we only had 28.9% of the specimen remaining, with that alone, we can find that this specimen is 10,208 years old. So it's just knowing how we can manipulate the formula to fit this percent. And off to the last one. All right, so I want to lead into this by saying rocket science is much more complicated than what we're about to make it. The formula that you see in your formula sheet is much more complicated than what you're given. I had to kind of condense it down the best that I could. But in this problem, looking at, well, let's just read it. A new liquid-fueled rocket has a burnout velocity of 9.49 kilometers per second and an exhaust velocity of c equals 5.2 kilometers per second. If the weight after burnout was 6,000 kilograms, determine the weight of the rocket prior to launch. So just so you know what burnout is, because you might not know what that term represents. Burnout is, in this case, it's referring to the moment when all of the fuel has been used up. So the velocity once all of the fuel has been used up is 9.49. The weight after all of the fuel has been used up is 6,000 kilograms, okay? So we're dealing with velocity of a rocket, so using our formula sheet and as seen above, we see that we get V equals okay. So, writing down what we're given. We have the velocity after burnout, 9.49. We know the exhaust velocity. So we're essentially saying that this is the velocity at takeoff. Okay? And then we have the weight after burnout. Okay. And we notice that of the 4 variables in our formula, the one that we do not know is the weight prior to takeoff. That's exactly what they're looking for, so that's good. We picked everything out of the problem. So putting everything in, 9.49, 5.2, natural log of W sub t divided by 6,000. Okay, so now we have a logarithmic function. That's why we've waited so long in this video to see this example. We have a logarithmic function. So logarithmic function, I have to get this term by itself, which requires us to divide by 5.2. So we divide by 5.2, giving us 1.825. Okay. So we do that. So unlike the exponential functions where we take the logarithm of each side, here we have to exponentiate each side. And what that means, because I still feel like some of us are not quite understanding this, is in order to remove this natural log, I must raise both sides using the base of e. So my problem would look like e to 1.825, and then e to the natural log of that. Okay, that's what it means when I say exponentiate, using the base of e. Doing so removes this natural log, giving us W sub t divided by 6,000. And we want W sub t, so we just multiply both sides by 6,000. And in doing so, we find that, should we do this in here? Yes, okay. So we get 6,000. We will multiply by E. So E is right with natural log. So I have to hit second natural log. 1.825. And we get 37,216.77. Okay? And this is kilograms. So that's, this is 37,000 kilograms before takeoff. And once all of the fuel has been used up, the rocket only has a weight of 6,000 kilograms. So I did some manipulations using conversions, just to give you an idea of how large this is. This here is roughly 82,062 pounds. And then using another conversion, this would also relate to 41 tons. So it's just something to kind of relate to. That's a lot. That's a lot of weight. It's a rocket with a lot of fuel. But in the end, what we are really concerned about is knowing what formula we're using, knowing what we are given, and knowing exactly what's needed to solve. Hoping that we have everything that we need, that we just plug it in and solve. Those are the ones that we want to have. So when you enter, there's a longer video than normal, but when you enter class, we're going to be practicing each of these, because each of these have a different formula, and each different formula requires some minor differences in solving it.